Okay, so we spent the last 2 days learning rate laws. Reactants raised to some power. But the problem was the rate law doesn't always match the stoichiometry. So we have to go in and experimentally determine it. So if the rate law doesn't match the stoichiometry, what the heck is the rate law telling us? Well, today we're going to talk about reaction mechanisms. For any general reaction, A plus B goes to C plus D. We never use the products, we only use the reactants. So we might expect that the rate is K, A to the A power, B to the B power. But we know that's not true. It's N and M, where they may or may not have anything to do with A and B. Sorry, I love Minions. My office is a mess, but on one of the windowsills I have the Minions chemistry factory for making their jelly. I love Minions. Okay, so if N and M don't match A and B, where the heck do N and M come from? Where exactly are those exponents coming from? Well, they come from collision theory. Collision theory tells us that molecules have to bang together in order to react. But collision theory does not tell us which molecules bang together in which order. What we're going to look at today with mechanisms is how are the molecules in the reaction actually colliding. So we know the rate of the reaction is reactants only, but it's not necessarily the reactants written in the overall reaction that are colliding. The rate of the reaction depends on the actual mechanism of which molecules collide, how do they collide, what order do they collide in. So the problem is reactions don't have to occur in one step. There can be multiple steps where A reacts with B, but then B then reacts with another A. And it's more complicated than just saying A molecules of A and B molecules of B combined together. We have to have the molecules literally banging into each other, but our rate law tells us which molecules bang together to create the reaction rate. Now we'll start with reactions that we know are a single step. The reactants all combine in one step. We can collide. Okay, we do have ones, it says occur in collision of two or more. We have ones where only one is necessary, but it has to collide with something. Usually it collides with a photon. But we want all of this to occur in a single step. If that's the case, then the reaction rate law is the stoichiometry. If everything's banging together in one step, then the stoichiometry is telling us what the reaction mechanism is. So for an elementary single-step reaction, elementary means a single step. Those two words are the same. Elementary is single step. The rate law does come from our balanced equation. We're going to talk today about the molecularity of the reaction. The molecularity of the reaction is how many molecules bang together in the step that the rate law is looking at. Molecularity is the same thing as order of the reaction. A first order reaction is one molecule. Second order reaction is two molecules. Third order reaction is three molecules. We're not going to do zero order here because I told you those are really weird. But the molecularity of the reaction tells us how many molecules are banging together when the reaction begins and is the same as the order of our reaction. So first order, we're going to refer to as unimolecular. Second order, bimolecular. Third order, termolecular. So unimolecular is the same as first order. It means that AB falls apart without colliding with another reactant. My rate law is just KAB. As I said, it usually collides with something, most frequently a photon, but it falls apart without banging into another molecule. Sometimes things fall apart for no reason at all. Well, they usually have a reason. They're too hot, or there's sunlight, UV light on them or something. But they are not banging into another reactant molecule. So, as I said, usually due to heat or light. So, unimolecular is rate equals K times AB, which is first order. So we're now defining the orders by how many molecules are banging together to create the reaction start. Not the entire reaction, but just the start of the reaction. For an elementary single-step reaction, that is the entire reaction. Bimolecular means A and C collide to react. Two molecules are coming together to react. I don't even know what those molecules are supposed to be, but it was a cute cartoon. So, bimolecular, for A and C banging into each other, the rate is K times AC. But I can have a bimolecular one in which two of the same molecules bang together, and then my rate is Ka squared. This is exactly the same as second order. So we learned all the orders of the reactions and how to find them. Now we understand what the order of the reaction is telling us. Or at least we're supposed to understand. Hopefully by the test you'll understand. Termolecular means three molecules are going to collide at once. I had hydrogen and oxygen making water up here. This is a termolecular reaction. Two H2s and an O2 all bang together at the same time. So termolecular, A times B times C, or in the case of water, A squared times B, H2 squared times O squared, or A cubed. All of these are examples of third order reactions. So in a single step elementary reaction, we can say that all of the reactants, no matter how many there are, all bang together in one single step. And they are either unimolecular, bimolecular, termolecular, or we can go higher than that, but we're not going to because it gets too complicated. So if these are elementary reactions, then the stoichiometry is what matters. So for the first one, there's two NO2s, so that has to be KNO2 squared, and it is bimolecular. Now, like I said, we're looking at elementary single-step reactions, so the stoichiometry works. For B, I just have K times SO2Cl2, and it's unimolecular. That molecule is fairly unstable. Shine light on it or heat it up, and it does fall apart on its own. For the third one, I have two atoms of chlorine and a molecule of N2, so Cl squared N2, that is a termolecular reaction. And for the last one, I have ozone plus chlorine going to oxygen plus ClO. Oops. I carried down and copied, and I shouldn't have. Ozone times Cl, so bimolecular. You guys are all too young to probably have heard of this, but back in the 70s and 80s, there was this real concern about a hole in the ozone layer in the atmosphere. Somebody's heard of it. Will and Greg have heard of it. Peyton's heard of it. Good, I'm glad some people have heard of it. Well, they rationalized that what was causing it was this reaction. Things that we had in aerosols were releasing chlorine and fluorine atoms. And when they reacted with the ozone, they produced oxygen and this ClO or FO, and we're destroying the ozone layer. It's why all of our antiperspirants and all of our freezers with Freon in them and our air conditioning units all had to be changed. And they said, this is going to be a lot better. And I will tell you, it's not a lot better, but it's slower at destroying the ozone. We have this tendency in chemistry to say, oh, this is really bad, so let's try this. And sometimes this is not better than that. Like I said, what we're using now is simply slower. But that was a really important reaction back when the EPA started doing studies. Again, nothing to do with this chapter, it's just you should know that there are uses for some of these things. There are times where these reactions are important. Okay, unfortunately, we can't always determine the rate law from the stoichiometry because not all reactions are elementary single-step reactions. Some of them take multiple steps to occur. So if that's the case, we need to know what is the mechanism of the reaction. How are the molecules banging together in each step? So we're going to assume a reaction consists of two elementary steps. It can do more. I told you last week that one of the ones that I have upstairs in the lab actually takes 12 steps. I have another one that takes 7. But we're going to stick right now for 2 steps. So we're simply going to say, this is what the rate law looks like. And we're going to use that rate law to define what the first step must look like. What is actually banging together in the first step that produces that rate law? So I have AB plus C going to AC plus B. I'm going to say that the step is that AB dissociates on its own, and then A reacts with C to make AC. I've got the B already made from step 1, and then I create the AC in step 2. Each step is going to have its own rate law. So the rate law for step 1 is, where's my pen? The rate law for step 1 is K times AB. The rate law for step 2 is K times A times C. Now, if we look at an energy diagram and look at what the activation energy is, the activation energy is a lot higher for the first step, A, B, decomposing into A plus B. That slow step is going to mean that that is the step that gives me my rate law. It's the one that creates the bottleneck in terms of things reacting. It's slow to create A plus C is very fast, but if I'm slow in creating A, then A and C aren't going to react very fast because I don't have a lot of A. So not only do I need to know what's banging together in each step, I need to know how fast each one of those steps is. So what determines the rate law? Okay, I found this online. Laws of physics. Here's a law that is applicable to everybody and everything in the universe, laws of chemistry. Here's a law only for 2 elements, and there's exceptions to everything. It's true. We give you things. We call it a rate law, but it doesn't always work. But we're going to just accept the fact that it works for everything we're doing in this class. So what determines the rate of the reaction is what we refer to as the rate determining step. The rate determining step is the slow step of the reaction, the one with the greater activation energy. Now, for the one we just saw, AB going to A plus B was the higher activation energy, so it was the slow step. So that reaction, step 1, is what is determining my overall rate law. So slow step, high activation energy, that is what's determining my rate law. So if that's the case, my rate law for that reaction was rate equals K times AB. Despite the fact that my stoichiometry is AB plus C, my rate is determined only by AB falling apart. So my rate law here does not match my stoichiometry because C isn't involved in the slow step. So that's my activation energy. That's my activation energy. You can see the difference between the two, and the one with the larger activation energy determines the rate. So let's look at this reaction. Nitrogen dioxide and carbon monoxide make nitrogen oxide, monoxide, and carbon dioxide. And the rate is NO2 squared. There aren't even two NO2s in the stoichiometry. So what the heck does this mean? Well, what it means is that my first step is actually two NO2s banging together. I don't know exactly what my mechanism is, but I can make a guess. So I'm going to suggest a mechanism. And I'm going to suggest that it consists of two elementary steps just to make it easier. And I'm going to say I have to match the rate determining step. So my rate determining step, the slow step, has to be two NO2s banging into each other. So what happens if I bang two NO2s together? Okay, I'm just going to make the rate determining step the first step of the reaction. And I'm going to say the two NO2s bang together, oxygen moves from one to the other, and I get NO, which is one of my products, and NO3. But now NO3 is going to react with the CO. I'm going to go back to NO2, and now I've got a CO2. Each one of these has its own reaction rate. Now, first thing I need to make sure is that when I write a two-step reaction, the overall reaction is correct. So NO3 cancels out, and one of the NO2s cancel out, and overall my reaction is NO2 plus CO goes to NO plus CO2. So the first thing I need to make sure is, do the steps match the overall reaction? And the second thing I need to make sure is the slow step matches the rate law. So I'm making that one slow. I'm going to make that one fast. Once NO3 is created, NO3 is very unstable. It reacts easily with the CO, and that reaction goes very fast. So now this is what my energy diagram looks like. I start with reactants, I end with products. I have the transition state for step 1 and a transition state for step 2, and in the middle I have an intermediate. The intermediate is a chemical that I produce that is not a reactant or a product, will be formed in step 1 and immediately used up in step 2. So my intermediate for this reaction is NO3. Because if I look at my reaction, NO3 gets formed in step 1, it gets removed in step 2. That is my intermediate. So my mechanism makes sense. It's plausible. It matches the overall reaction. It matches the rate law. Those are the two things it has to do. Am I right? Am I wrong? I have no idea. I could be right, I could be wrong. The problem is that I know the mechanism matches the rate law, but there might be other mechanisms that match the rate law too. And if I can't tell the presence of an intermediate, I don't know that NO3 has formed. I don't know that some other intermediate might not have formed. Is there a way to show if my mechanism is correct? Only if you can see the intermediate. Okay, so my reactant is a bluish purple. I'm going to add sugar to this. And it turns green. Then we'll let it stand, it turns red. So I know what the steps of this reaction must be because I see the green color and I see the red color. And in the end, it's yellow. So I start with indigo carmine, which is the dye of your blue jeans. I let it sit, oxygen oxidizes it to red, then to green, and then the glucose reacts and turns it yellow. So I know that there are intermediates in there because I can see colors. Then when I add more oxygen to it, it goes back to the green color. This is the only way to know if your reaction has the correct intermediates or not. That's called the stoplight reaction because it goes from red to green to yellow. But that's the only way I know if my mechanism is right, is if I can see intermediates. And then I can say, okay, I know indigo is that bluish purple. What happens to turn it green? What happens to turn it red? What happens to turn it yellow? And then I've got 3 distinct steps that I can match. For the most part, when we make a mechanism, all we want to know is that the slow step of the rate law matches the overall rate law, and that the stoichiometry of steps total to the balanced equation. Okay. My laptop at home has no G or H. Can you tell? There's an H in stoichiometry. It's fun at home. My laptop doesn't have a G, an H, an up arrow, or now it doesn't have an escape button. I need a new laptop desperately. Okay, so these are my rules. I have to know that my mechanism overall matches the stoichiometry, the balanced equation, and that the slow step matches the rate law. Okay. So I've got a reaction here where I say NO plus Cl2 goes to NOCl, and I want to know what that is. So my overall reaction here is 2NO plus Cl2 goes to 2NOCl. My intermediate is created in the first step and used up in the second step. So my intermediate is NOCl2. And despite the fact that the overall reaction is 2NO plus Cl2, if the first step is my slow step, then my rate is equal to K times NO times Cl2, and it is bimolecular. Okay, I don't know if anybody looked at any of the review things for the exams over the weekend, but I realized that I didn't have any mechanism questions in there, so I posted 2 new multiple choice, the multiple choice and the multiple choice with answers that include things like this. What is the intermediate in the reaction? Okay, so what is the molecularity? Well, we just wrote the rate law. The rate law is NO times Cl2. That means two molecules are banging together. So assuming the first step is the slow step, then it's second order or bimolecular. Remember, the order and the molecularity mean exactly the same thing. Now, based on this diagram, where are the transition states? Well, the transition states are at the top of every single hill. So that's a transition state, that's a transition state, that's a transition state. So there are three steps. A goes to B with a transition state, B goes to C with a transition state, and C goes to D with a transition state. My intermediates are B and C, because overall I'm only going from A to D. My intermediates are B and C. Now looking at this diagram, which one is the slow step? Is it the first step? What determines the slow step? Xavier's not here to answer all the questions.
The relative activation energy, the one with the highest.
The one with the highest activation energy. So which one has the highest activation energy?
Third.
The third one. The first step is not the slow step. The third step is the slow step. What do we do then? Okay, so the highest activation energy is the slowest step, so that is the rate determining step where C goes to D, and overall, the reaction is exothermic because A is higher than D. Okay, this rate, this is a complexation compound. We will talk about complexation in the end of chapter 17, I believe. Transition metals have a bunch of d orbitals. And when they lose their electrons, most of those d orbitals are empty. So if you put them into something that has lone pairs, then those lone pairs are going to attach to those empty orbitals. And so they make these things called coordination complexes. It works with water, because water has lone pairs on the oxygen. It works with cyanide, because there's a lone pair on the nitrogen. It works with ammonia. It works with a number of things. We want to replace that water with an iodine. But this is a single-step reaction with a rate law. Well, it's not a single-step reaction. It's going to be a single-step, slow step 1 reaction. So we're going to say that step 1 is probably that COCN5H2O minus 2 simply loses the H2O. The complex decomposes by itself without banging into anything. The iodine will then come in at the second step, where this now reacts with the I minus to create the COCN5I. And now overall, we're minus 3. I don't know if that's right or not, but it makes sense according to the rate law. I am not on a test going to ask you to come up with a rate law, come up with a mechanism. But I will ask you on a test, does this mechanism make sense for this overall reaction? Does it match the rate law, and does it match the overall stoichiometry? So that was what I assumed must have happened with the first step slow. But as I just said before I showed that slide, with the one that we had that had 3 steps, the third step was the rate determining step. So what do we do if step 1 is not the rate determining step? Well, now I got a problem because the rate determining step always defines the rate law. So this reaction, NO plus Cl2, has a reaction rate that's NO squared times Cl2. It looks like it's termolecular, except we know termolecular reactions are rare. So we could make a mechanism that said, okay, this matches this rate law, but it doesn't require three things to bang into each other. And the mechanism that has been suggested for this particular reaction is not a termolecular, it's a multiple step one. So what they suggest is that NO reacts with Cl2 first to make NoCl2, which then reacts with the other NO and transfers the Cl. The problem is the first step goes very fast. The second step is the slow one. It's the rate determining step. So my rate law has to have the reactions from step 2. NO, NoCl2. Got a problem there. What is the concentration of NoCl2? It forms, it disappears. I can know what the concentration is of the reactants because I put those in. But to create an intermediate and then lose it, that's a changing concentration. I can't put in a concentration for that because it's not a constant. I don't know what it is. So I've got a problem here with my rate law. So I have to make some assumptions. Because the rate of the reaction is not dependent on an intermediate. It cannot be dependent on an intermediate. And so the one I have can't be right. So if the second step is the rate determining step, I'm going to say that there's time for the first step to reach equilibrium. Now, I love that they say this now, and we don't define equilibrium until tomorrow. But equilibrium means that that reaction is going so fast, and it can go backwards as well, that it reaches a point where the concentration of both the reactant and the intermediate have stabilized and are constant. Now I've got a way to find that concentration of that intermediate. So as the reaction proceeds, we know the reactant disappears. And it becomes harder and harder for the reactant to continue on. So we get to a point where we look at this, and it looks like the reaction has stopped. The reaction has not stopped. It's simply gotten so slow because the reactants can't find each other that it's hard to detect the changes. But as that happens, my product has built up. And if my forward activation energy is about the same as my reverse activation energy, then it's actually easy for once the products are produced for them to start reacting and go backwards. So as product appears, it is possible that they can begin to react and send the reaction in a reverse direction. This does not work for everything. It only works when my activation energy is not super different between the forward reaction and the reverse reaction. Because in a reaction in which I see this, my activation energy for the reverse reaction is huge in comparison to the forward reaction there. That is probably not going to go in reverse. But between like here and here, those activation energies are almost equal, which means that going forward, going in reverse would be easy for those steps. So I'm going to have My reaction's going to products, but now I'm going to have products going back to reactants. And they will continue to do that until the reaction stabilizes and the concentrations of both the reactant and the product in that step stop changing. This is referred to as a reversible reaction. And we spend 15, 16, 17, 18, 19, talking a lot about reversible reactions and equilibrium that occurs in reversible reactions. But the problem with chemistry is we tend to introduce things and not explain them till later. Like we introduced orders of the reaction and what a rate law means, but we didn't explain it for 2 more days. I'm introducing the concept of equilibrium and we'll not go into it in detail until tomorrow. So just have to accept that at this point, a reversible reaction is one in which reactants go to products in a forward reaction, but products go to reactant in the reverse reaction. Now, at this point, the concentrations have stabilized, but the concentrations aren't constant. What is constant is the rate of the forward reaction versus the rate of the reverse reaction, which means every time an A makes a B makes an A back, which is how my concentrations can remain stable. Equilibrium says that the rate of the reaction is equal both the forward direction and the reverse. So rate 1 is equal to rate minus 1. So I'm going to set up 2 rate laws for this fast reaction, a forward one and a reverse one. So my forward one is K1NoCl2. My reverse one is K minus 1 times NoCl2. But the definition of equilibrium is that rate 1 equals rate minus 1. So these 2 things are equal. Now, I know what the concentration is of my intermediate with respect to reactants that I know what the concentrations are. So the concentration of my intermediate is K1 times NO times Cl2 divided by K minus 1, and K1 over K minus 1 can just become a single K value. Okay. So this is how I can say my rate is dependent on a second step, which is slow, which is dependent on an intermediate, but I now know how much the intermediate is because I've allowed the reaction to produce a constant amount of that intermediate. Now, we had to make the assumption that the slow step was slow enough that it allowed the first step to do this. If it doesn't, then there's no way we can solve this. So now I'm going to put that NoCl2 into the rate law of the slow step. So my slow step was here. So now for this, I'm going to substitute in a K times NO times Cl2, which is what I got from the equilibrium. Now I got a bunch of Ks here. But they're all constants. I can put them all together. So now I have KNO times what would have been NoCl2, which is now K1 NoCl2 over K minus 1. But all those Ks are constants, So I'm just going to say the rate is K times NO squared times Cl2. So even though this looks like a termolecular reaction, this mechanism suggests that it doesn't have to be. It can be a two-step bimolecular reaction where the second step is the slow step, as long as we allow the first step to create a situation where the concentration of the intermediate has become a constant. Now, which one's correct? I don't know. The only way to know whether or not this is true or not would to be know something about NoCl2. Okay, NoCl2 is a yellow gas, but so is Cl2. So I don't know the difference in the color between, this is nitrosyl chloride and chlorine gas itself. If there's a slight difference in the yellow color, we might be able to see it. Otherwise, we might just see yellow and we don't know. So we've now created a mechanism in which the rate law looks termolecular, but isn't. This is what people think it looks like. It looks like it's straightforward. What it really looks like is this mess in the middle. Okay, so the reaction of NO with oxygen has several proposed mechanisms. None of them are truly known because we don't know what these things are. Again, I would need to find NO3. And if I look at NO3, it's colorless. If it's colorless, I'm not going to see it form. So that's why there are several mechanisms proposed for it, because we can't check any of the intermediates, so we don't know. So overall, the reaction is 2NO plus O2 goes to 2NO2. My two-step reaction matches the mechanism because NO3 is an intermediate, so it matches the mechanism. And if the second step is slow, then my rate would be NO times NO3. But now I've got to go back to the NO3 and set it equal to something according to NO and O2. So the rate forward is NO times O2. The rate reverse is K times NO3. I set those two equal. NO3 is now some K value times NO times O2. Replace that into the slow step, and I get K equals NO squared times O2. Remember, the important things here is not for you to come up with a mechanism, but for you to recognize that the mechanism matches the overall stoichiometry, and the slow step matches the rate law. And if the rate law is a result of the second step, and it includes an intermediate, you must replace the intermediate. Okay. So the PhET simulation I could find was all about catalysis, and we haven't talked about catalysis yet. So I went back into this guy. And I just looked at, okay, I'm going to choose a reaction. I can have an angled shot. I'm going to Okay, that's what I want. Okay, I'm going to set a certain number of each one of these things. And notice, I now see that energy diagram. Now that energy diagram means that the total energy of these molecules at this temperature is pretty large. The energy is pretty small. None of them reach my activation energy. So as I look at those molecules, they're just bouncing off of each other. They're not doing anything. Now, if I increase the number of molecules, I still see them just bouncing off of each other. So how do I get this reaction to occur? Well, I get this reaction to occur by increasing the temperature to the point where my activation energy is very low. Okay, so now what I'm looking for is a yellow against a purple and a gray that's all by itself. And I can see now that there's a gray that's all by itself. There's a couple more grays by itself. So by increasing the temperature, that is the only way that we're going to affect the rate of the reaction, because it allows more of the molecules to reach the activation energy. Okay, it's 10 o'clock. Let's take a 5-minute break, and I'll finish with the last topic from chapter 14. And I apologize that it went all the way to 10 o'clock before I gave you a break, but we started 10 minutes late because of the computer problems. Pause that. Okay, so the very last thing in chapter 14 is, we know that the reaction rate is dependent on the surface area. So if I have a solid, if I smash it up into smaller pieces, it will react faster. We know that if we take like big lumps of sugar and try and dissolve them, it works better if you smash up that big lump. We know it's dependent on concentration if it's a solution. We have found that one way to change it is to increase the temperature. But the last thing that we listed it was dependent on was the presence of a catalyst. Catalysts work exactly the way the picture shows. The hill represents the activation energy. And that truck has to get up over that hill and over the activation energy. But the catalyst is, let's drill a tunnel through the mountain. Let's find a way to avoid that activation energy. So what a catalyst is a material that is added to the reaction, but it's not consumed in the reaction, which means it goes in as a reactant, it reacts in my first step, but then in my second step, it comes back out unchanged. So what is the purpose of a catalyst? It works by decreasing the activation energy by taking a single-step reaction and making a two-step reaction with smaller activation energies for each. Now, it's a lot easier to get from reactants to products through that blue path as opposed to the red path. So that is the purpose of a catalyst, is to convert a single-step reaction into a multiple-step reaction that then reduces the overall activation energies. So here is a reaction of sulfur oxides and nitrogen oxides in air pollution. Okay, nitrogen oxides are produced because the car engine or the industrial plant or whatever is hot enough, it's actually reacting the air, reacting the nitrogen and the oxygen in the air. Sulfur dioxides are produced when your fuel is sulfur heavy. Not a big deal, not as big a deal now. 20, 30 years ago, diesel was cheaper than regular gasoline, so lots of people bought diesel trucks. But if you were behind a diesel truck, it was spewing out really nasty, ugly pollutant stuff. Somebody's going, yep, I remember that. It had to do with the quantity of sulfur in the diesel fuel. It wasn't as refined as gasoline was. So they started taking the sulfur out because sulfur was reacting with the air and making these sulfur oxides, SO2 and SO3. I lived for a while in a place where there was an oil refinery, and there were outside the oil refinery hills of yellow stuff. That was all the sulfur they were removing from the oil. But it also made the process more expensive, which is why now diesel fuel is more expensive than gasoline, and everybody regretted buying their diesel trucks. The reason we don't like SO2 and NO2 or SO3 and NO3 or any of these things is not just because they're bad for us, but when combined with a humid atmosphere and water in the atmosphere and clouds, they create acid. And then you've got sulfuric acid and nitric acid, which are pretty strong acids, in your clouds and then in your rain. So I'm just telling you why we don't like these guys. But when they're present in the atmosphere, they can react with one another and pass oxygens back and forth. So SO2 can react with NO2 to make SO3 and NO, then NO can react with oxygen in the air, makes NO2. So overall, if I look at what's going on, my overall reaction is 2 SO2s plus 2 SO3 goes to, 2 SO2s goes to 2 SO3s plus an O2. Now that's actually good because, hang on a second. Because it's actually giving us oxygen back. But SO3 is nasty. SO3 does create sulfuric acid, so we don't like it. But now, you'll notice there are two different types of things in here. There is a catalyst, and there is an intermediate. The intermediates are things that are produced in step 1 and used in step 2. So they're products in step 1 and reactants in step 2. That is NO. NO is an intermediate. But NO2 is a catalyst. Catalysts are reactants in step 1 and products in step 2. So catalysts are things that I add at the beginning that come back out at the end exactly like they started. Intermediates are things that I make and then use up and they disappear. So this reaction has both intermediates and catalysts in it. Now, catalysts are extremely important in everyday life. We use them in chem labs all the time, but they're also very useful in other things. We have homogeneous catalysis. Catalyst is the noun, catalysis is the verb. Homogeneous catalysis means that it is happening in the same system, usually a solution. You put something into a solution to make the reaction go faster. Hydrogen peroxide. If you buy hydrogen peroxide from the store, it's in a brown bottle, and they tell you to store it in a cool, dark place because it naturally decomposes to water and oxygen. It's why when you put it on a cut or something to clean, it bubbles. That's the oxygen gas it's producing. And we know that it reacts because we can test that gas for oxygen. We test for gases that are produced by using not a lit splint, but one that's just got embers on it. If oxygen is present, it will cause it to flame. If hydrogen is present, it will cause it to react. It increases the temperature of the hydrogen, so it reacts with the oxygen and you get a pop. If it's CO2, it simply puts the embers out. So this is a way that we test for the presence. So we know that oxygen is being produced because it's causing that ember to flame. This actually is catalyzed by the presence of a strong acid. HBr here simply because it's not as bad as HCl, and HBr is fairly easy to get. It's used in veterinary medicine, so it's fairly easy to get. But if I put it in with the hydrogen peroxide, the first reaction I get is that the bromine breaks off to make elemental bromine. And then H2O2 reacts to make an H2O. But then I take a second bromine and I take the bromine, I react it with a second H2O2, and I get the oxygen out, and I get HBr. So again, I have a catalyst and an intermediate here. So I can catalyze this reaction, and Br2 is an intermediate because I'm making it in step 1 and using it up in step 2, but HBr is a catalyst. I got to learn not to lean on this because I'm using it in step 1 and it comes back in step 2. In this picture, you can actually see, it's actually dark brown, not black, but you can actually see Br starting to form. But then, you can see it starting to disappear. Iron metal will do exactly the same thing here. But we just need something that we can put into a solution. In the chem lab, we want things to go faster. We simply add something that will speed it up. The second type of catalyst we have is a heterogeneous one. That is one in which the catalyst you put in is in a different phase than the reaction you're doing. Now, most of you use a heterogeneous catalyst on a regular basis. We talked about solutions at the beginning of chapter 13, and I said you can make a solution with a gas into a solid, and it is hydrogen gas into palladium or platinum. That is your catalytic converter. The purpose of the catalytic converter is to literally slow down molecules. Coming out the exhaust are some of these nasty nitrogen oxides. NO, NO2, NO3, N2O4, N2O5, all of these things because nitrogen's reacting with oxygen. There's also carbon monoxide that gets produced. So they're coming out very, very hot and moving very, very fast. But this catalytic converter, with all of these solid spaces with the hydrogen leaving little gaps in the metal, slows the molecules down. It gives them a surface that they can sit on and allow the other molecules to find them. So it converts your carbon monoxide into carbon dioxide. It converts your nitrogen oxides into N2O. I don't know if N2O is better than the other nitrogen oxides. That's laughing gas, but I suppose it's better than the brown stuff that comes out the back end. I don't know. And water. So this is a heterogeneous catalyst because we're using a solid to catalyze reactions of gases. These are just a bunch of different reactions that occur at your catalytic converter. CO, HC, which is a methyl radical, NO. All of these are trying to react to produce less toxic things. These are all the things we expect to be happening in your catalytic converter. Now, probably the most important one of these catalysts is your biological catalysis. If it were not for enzymes, which are catalysts in your body, most of the reactions that occur in your body could not occur in your life expectancy. Enzymes are required to catalyze the reactions. They work on a process not dissimilar to what the catalytic converter is doing. It provides a surface to trap something. Your enzymes have very specific shapes to them. It's a lock and, if you've taken biology, you know it's a lock and key mechanism. Only certain reactants, biology has to use certain different words. We do. A substrate is just a reactant. It will latch onto a certain reactant, create this intermediate, your enzyme substrate complex, and then either allow that reactant to break apart and produce products, or allow a second reactant to find it because it's slowed it down enough, and so I can bring in another reactant, whatever that is, and allow it to react. And it does this simply by doing the process of converting a single-step reaction to a two-step reaction. In this case, the enzyme catching the reactant is very, very fast. It's the equilibrium. The second step, where the substrate reacts either by itself or with something else to give you your enzyme back and a product, is my slow step. But without that catalyst, S to P could take hundreds of years. We need these enzymes. This is what it does. Huge activation energy for the reactant going to the product, much lower activation energies with that intermediate. Okay, so tomorrow we will start chapter 15. Chapter 15 is not on the test. Up to today is the only thing that's on the test. So, as I said, if I go into a student preview, go to your exam reviews, and you'll see the list of topics that I expect to cover on the test, a PowerPoint with examples of problems, but also some examples of just things you should know, like what is solubility. But all of these have questions in them, and none of them are answered, so I have an answer. Now, the reason I'm still talking is because I want you to look at this guy, because most of this stuff makes sense. It's all stuff I've covered. But this part will have a bonus question. And the bonus question is, can you convert between one type of concentration and another? So I have a brand of wine that is ethanol, labeled 13.5% volume to volume. That means milliliters to milliliters. Given that the density of ethanol at room temperature is that, what is the molarity? The second one gives you a molality and wants you to find a molality if you are given a molarity. So for this, you have to figure out exactly what it is that you need to do to convert. So to convert between volume to volume percent, first thing I needed to do was say what that meant, 13.5 milliliters of ethanol and 100 milliliters of solution. 135 milliliters, oh, that's 135 milliliters per liter. 135 milliliters times the density of the ethanol is 106.5 grams of ethanol, which then converts to 2.31 moles. And so there's 2.31 moles of ethanol in that 1 liter. To go from molality to molarity, or molarity to molality, whatever it is I'm doing here, I use the density in a different way. Instead of using the density just on the solute, I use the density on the whole solution. And I get what are the grams of solution. So what I'm looking at is a 4.3 molar solution with a density, and it's salt. So I have 4.2 moles in 1 liter. I convert that and find out that that 1 liter is equivalent to 1,050 grams of solution. I find out how many grams of NaCl there are in that many moles. I subtract off that number of grams from the total grams of the solution, and I take the 4.20 moles of NaCl and divide it by the total kilograms of water that I had. So you need to know what it is you're given in terms of moles, liters, grams, whatever, and then figure out how to convert that. This is not a required question. It's not going to be something you have to do, but I always put one of these bonuses in just to see if you can figure. It's an extra 5 points on your test if you can figure out how to get from one concentration to another. Okay? That's the reason I was still talking, even though I finished on the lectures. So review all of these exam reviews, and if you still feel like you need more practice, there are multiple choice practice problems and suggested problems from the end of the chapters. Okay, as I said, tomorrow we will start chapter 15. It is not on the test, and I don't have your lab up for Wednesday yet. I need to go get that up because I was busy trying to get these things up. So I will go do that. Nobody here missed any labs last week, right? Everybody was here. Okay. Just need to make sure I don't need to do makeup labs for any week. Okay, so I will see you tomorrow morning. Have a good afternoon. It's supposed to be really nice this afternoon, so enjoy the weather. Give me 1 sec.